Hello, this is an introductory video to help you understand when to use feedforward control strategy as a part of the line project. Here we try to present an industrial example. So a good example could be a crude oil fractionation section of a typical oil refinery, where the final product or finished product are naphtha, residual stream from top and bottom of the fractionator, gas oil, and others. The example has been taken from the book of Professor Organic and Professor Ray, Process Dynamic Modeling and Control, Oxford University Press. Here is perspective of the oil refinery. On the left hand side you have the tank of crude oil that could be different, light oil, heavy oil, oil from different countries, so could have different characteristics, and they are fed through pump to the heater or furnace, and the heater had to heat up this crude oil to some boiling point situation and then deliver it to the fractionation section or fractionator, and then fractionator finally give different product from different sections of this fractionation. So this is the general aspect of oil refinery. We want to focus on one of the important aspects of this one, which is this heater or this furnace as an industrial control problem. This is the furnace in the middle that you saw. So the crude oil comes with some Fi, flow rate Fi, and temperature, initial temperature Ti, and then need to be heat up to some Fo and To. So the Fo and Fi will be defined by fractionation, but the temperature, delivered temperature, is the objective. So the objective is to deliver the crude oil feed to the fractionator at some constant temperature. These are set point value. But this could happen regardless of the condition of the furnace. But what are the conditions of the furnace? First, for safety reason, we have to be careful to have not the temperature of the furnace go beyond some limit because of the metallurgical limits of the furnace tube. The crude oil at the beginning, at the start, at the inlet, had some initial temperature Ti that substantially changed during different times, so it's act like disturbances. Also, the heat content of the fuel and also the pressure behind the fuel valve could change, vary, so make act as disturbances as well. So these are the conditions, and with this condition, let's simulate a discussion between a plant engineer and a control engineer. So you have been asked, the plant engineer has called you as control engineer to get your advice how to improve the situation. And let's see how you need to proceed. The control engineer with the purple here, what are your operating objective, and the plant engineer explain what we mentioned about the delivery of the crude oil at some desired temperature to the fractionator, and also said that this value is a set point that will change every 2 to 3 days, and also you have an upper limit and something like that. So, and then the control engineer will ask about the Fo and T, the output, temperature, and flow rate. The former is set externally by fractionator, how much flow need in the fractionator, but T is actually about the desired temperature. And what is the control objective? It's say to regulate the process output temperature T as well as the servo problem. So regulatory problem means the set point is fixed, so you need to avoid or suppress the disturbances to keep it in the set point. Servo problem means changing set point. So it's our problem every 2 to 3 days is servo problem, but usually most of the time is regulatory problem. And then control engineer will ask about what do you have control over, and he explained that the fuel ratio the fuel to air ratio is our main manipulated variable, and the air valve is fixed, but the fuel will change, and this ratio will change, and this is our manipulated variable. And also ask about the disturbances, and we say the initial temperature of the crude oil and the flow rate could change, so act as disturbances. And then to ask about other disturbances, and it say yes, fuel supply pressure and fuel heat content also act as disturbances, because when the pressure behind the fuel valve will change, depending on how much you open the valve, different flow of fuel will enter. So by changing the fuel pressure, it acts as a disturbance. And finally, it will ask about what do you have for instrumentation. And here you will see, say we have thermocouples for measuring the temperature of T outlet and TI, flowmeters for measuring the fuel, oil, crude oil, and also the fuel. Also the control valve and optical pyrometer for the temperature of the furnace and alarm. These are the things that we have. So very good. And now let's see. The first question again in second phase is that the control engineer will ask, do you have a process model? He say, no, we don't, but we have a good operator. He understands very well this process, but his action is on the left figure, manual control. This operator, when do manual control, acts like this. So you'll see too much fluctuation around the desired temperature will happen. And the control engineer will ask, what do you think is the reason? So basically, the answer is basic human limitation. So we need some feedback control. We need some automatic control. And then finally, the control engineer suggests, okay, let's put a feedback control structure on the right-hand side figure. You'll see the feedback control, get measurement of the temperature of the final at outlet, set point T star, and give command to the control valve. You will see the feedback structure of PID. And for PID tuning, it suggests that start with proportional band of 70% and reset rate of 2. Proportional band, you know, is 1 over K, or proportional gain, times some constant, and also reset rate is 1 over Ti for the integral term, and derivative term is set to 0. So it's just some small proportional gain and a small term for the integrator, and then feel free to retune it. But with this PID based feedback control, this is what we get. So it's much better than manual control, but you will see at the initial stage, because of the disturbance variation at the inlet temperature of crude oil, feedback is not acting quite well for this early stage of disturbance. So what is the suggestion is, okay, let's implement a feed-forward control strategy. On the left-hand side, we say, okay, without feedback, let's implement a feed-forward strategy. So measure the disturbance Ti at the initial point, and based on that, give the command to the fuel valve. And this is feed-forward control alone. And this will suppress to some good stages from the initial disturbance, but cannot do a good action or good performance for the rest of the things, because it's only act for the disturbance, and only one disturbance that you measure, not all the disturbances. So the next suggestion is to activate the feedback system as well. So the right hand side is a combination of feed forward strategy plus feedback strategy, and you will see how these are implemented, and the final action is the combination of feedback and feed forward one, and you will see the result. So this is how we proceed to understand the problem and where to implement feed forward, and usually we use feed forward with feedback to be complete, and you will see much better result with this combination. I hope this has helped you to understand better.